Hello and welcome back to the Oxford MAT Livestream. My name's James and this is a sort of bonus episode on this programme where we've been looking at math questions to look at some more math questions. Hi everyone, hello, how's it going? It's been a little while. Yeah, so there's people talking about things in chat. Good to have you with us. If you want to join in with live chat, if you're here live, then you can join in by going to slido.com/OOMC, where I am assisted by a current student who is moderating stuff over there as things run through on here. Good. Okay, right, here we go. Quick disclaimers. We'll do the vote. Let's do the vote for how was your day. But oh yeah, okay. I mean, I launch it. Oh, it's been so long that I can't remember how to actually run a live stream. What am I doing? Did I begin the thing? Yes, begin the thing, please. There we go. Okay, I need to expand that to get the actual button to start the thing. There we go. So you can vote about your day. Quick disclaimers for what's going to happen in the next couple of hours on this episode of the MAT Livestream. I'm saying disclaimers. I would like to talk about the 4 long questions that we had this year. That's right, 4 of them. I'd like to talk about the 4 long questions and do bits of the solutions, like we've been doing with past paper questions, to look through these. I should warn you that I actually like these questions, and I'm going to talk about them, including reasons why I like them. I'm saying this because in the past, I think people have hoped that this is a sort of like a session where you meet up with your friends afterwards and everyone's like very angry about things or something, and that's not my tone at all. I don't know if you've picked up on my tone over the last however many live streams we've had, but I would like to try and tell you about some of the maths behind the questions. I think people in the past have found that somehow annoying, that I actually want to talk about these things. And I'm not going to talk about the multiple choice questions. So like last year with the Pearson VUE system, we're not releasing the multiple choice questions. I'm not going to show any of them on screen today. I'm not going to talk about them. And then 2 more disclaimers, I'm afraid. I'm not going to comment on how many marks people have got or what a sort of average score is. I know it's been a frequently asked question beforehand, but I'm not going to comment on average scores. There will be a feedback report at the end of the admissions round in January, which has got the kind of official statistics about the mathematics admissions test overall, but that's not happening today. There's just good news. I think you don't have to watch 2 hours of video hoping that I drop some numbers that you would otherwise get from an admissions report. I'm not going to do that. No, I'm going to wait for the admissions report. I'm also not going to comment on your marks, which, I mean, obviously I'm not going to single out you and comment on your marks, but also this is not a way for you to get your answers marked. If you can remember what you typed for a long question and you copy it into Slido chat, I'm not going to mark it for you. This is not a way to sort of get some insight into how many points you've got on the actual math. I just want to talk about the questions. I suppose I can reassure people, because we've had some people asking. I've heard there was a thread on Reddit about this. People have noticed that some people saw different questions. I mean, I'm going to show you 4 long questions, right? Which is twice as many as you might have guessed. And I think there's some discussion online. I just want to confirm that we're aware we did that we know that different people saw different questions. And obviously we're going to take that into consideration when we're looking at math scores. That we know that different people saw different long questions. The way I'm phrasing this in the math paper that I'm releasing is that there's a version X and a version Y. And we know which candidates saw version X and which candidates saw version Y. So of course we can use that information. I think that's what I want to reassure people, that even though I'm going to show you version X and version Y, there's no sense that those are the same question or under the hood or something, or that they're testing exactly the same number of marks on each topic or something. They're just some math questions. Right, I am not going to speak. So someone in the chat, just as I say, I'm not going to do a thing. Someone in the chat says please, and thank you for saying please, but I'm afraid that's what we've got. And then people find other ways of rephrasing it without saying please, which okay, nice. Chat is having an okay day really overall. That's nice to see. Kind of a 3.7 with an interesting like woo, and then down a little bit. I'm always watching out for people who vote 1-star or 2-star. There are quite a lot of you today. I will say that personally, I wouldn't watch this live stream. I know that's a weird thing to say on YouTube. Hello YouTube, here we are. If I were a student, I didn't like going through papers afterwards. I do it now for you because people seem to want it. It's extremely optional. An option that you have is to just forget about this and move on. That's an option that I think I would have taken. There's a lot of YouTube videos out there, and this one has a disclaimer at the start saying, I'm not sure. It's not sure it's for everyone. Okay, I think we've managed to get both opinions in chat as to this. We're gonna not have that one. There we go. And there's a question in chat about interview questions. So good news. If you're leaving now because you don't want to see Matt questions, in a few weeks' time, we're doing another bonus episode. I think it's 2 weeks from now. We're doing another bonus episode where we're looking at some interview questions. So looking forward towards what interview might be like. I did one of these yesterday. I saw someone in chat. Yes, there's one at the top. There's an anonymous person saying they're at a webinar that I did yesterday. Let's stop the poll so we can have chat back. And okay, so someone's at the webinar. There were loads of people at this webinar where I did an interview question. But don't worry if you weren't there, because I'm doing something similar for the MAT Livestream. I couldn't leave my MAT Livestream people without getting the same interview information stuff. So we're doing a bonus episode in a couple of weeks. Also around late November or maybe early December is when colleges are expected to send out interview decisions either way to candidates. So either shortlisting for interview or saying, sorry, not invited to interview. So there we go. Right, that was a webinar I did for, I think, Brasenose College and St Catherine's College. Don't worry about it. Don't worry about the webinar. It was a thing that I was asked to do, and I'm going to do many of these things, including a MAT Livestream one in a couple of weeks. Right, yeah, so don't worry. I'm doing another version of the webinar just for you and for everyone else on YouTube. There we go. Right, good, okay. Good question, actually. Should we start preparing for interviews even though we don't know yet? Why not, right? It can't really hurt, can it, to think about some more maths questions? If you like, I like using the same sort of preparation, really, to look at hard maths questions with stages. I think that's a good preparation because when I do an interview question, I'm trying to do things in stages to build up. Okay. And then if shortlisted, it's not just on interview. Tutors can look back at any information, including MAT score or any other information we have on the application. So it's not a final hurdle for the interview, it's more information. We get to actually do some maths with you, and just you, live. A little bit like the other way around. There's currently loads and loads of you and one of me. What if it was 2 of me? No, what if never mind. Loads and loads of me? That would be nice, wouldn't it? Loads and loads of me. I think opinion, no, I should just sort of, I'm doing this to try and undermine things a little bit or to try and reassure people, but at one point I checked and online the opinion was that the version X was much harder, and then I've checked and other people are saying version Y is much harder. As I say, I'm not going to comment. I'm not going to do average scores or things, sorry. Can the interviewers tell us your MAT score? I mean, they could because they have access to it. There's no point in asking them because you don't need that information. And also you will get that information because you get your MAT score at the end of the process. So at the end, when everything's settled, in January, you get access to your MAT score through the registration portal. There is no point asking your interviewers for your MAT score. What are you going to do? Right, okay. Jacob, thank you for the bridge. There you go. Somebody in chat says Wednesday diabolical. Right, okay. Mark schemes, by which I mean the web solutions document that goes through solutions, is coming out in January like normal. This is a kind of sneak preview of bits of solutions. Thanks to Jacob. As always, if you have concerns or you want to report things, then the best way to do that is by contacting Oxford, e.g. through some sort of email address. If you can find an email address for Oxford or for your the college admissions office at your college, you're welcome to do that. Slido chat is not great because it's going really fast. Which questions are you doing first? Well, I was just going to go through them, I think. 26x, 26y, 27x, 27y. If you want to grab a copy, I've put this on the MAT website. www.maths.ox.ac.uk/r/MAT will get you there. So that website, but without the live component. I was just going to do all four, I think. That's my plan. Cool. We consider everything. Ruben's right. We consider whatever we like. We don't have weightings and some algorithm that looks at all of these numerical data. We have humans making decisions. I still think that's important. I know that's becoming a bit old-fashioned in 2025, but I still think it's important to have humans looking at all of the data and deciding using their brains, and maybe having big arguments with each other. And I think this helps us get the best candidates at the borderline, where we've got tutors who really want to go and look out for people they want to make offers to, rather than just, I don't know what the alternative would really be. Okay, let's go, shall we? I think I want to talk about a diagram. A diagram with lots of lines in. So this is 26, version X. Here we go. I can still see chat, but just to make a little bit more space, pop. I can still see this going on. Ruben's done a direct link. Thank you. Right. Okay. So you've been warned. I'm just going to talk about questions, and I'm going to talk about them in a manner that some people might find annoyingly positive. I have received feedback on my style, but I'm not changing. Okay. So the question is about two diagrams. There's a diagram for the first three parts, and then a switch up where we talk about a different diagram which has a longer description, including a disclaimer like no other points. Right, that's it. That's your long. That's what you get. You get this sort of connection for parts 1 and 5. But let's not think about that. Let's think about this diagram for parts 1, 2, and 3. We consider a diagram formed of 8 points equally spaced around the unit circle. So maybe I draw a circle. I draw 8 points. That's not my best circle, but you know, there we go, 8 points. With each pair of points connected with a straight line. Well, okay, I've drawn a circle, but I'll pretend that's made of straight lines. And then each pair of points connected with a straight line, except, whoops, cases where the 2 points lie directly opposite each other. So I shouldn't have drawn that one. Oh, they've added a new sort of eraser on my row, which catches me out. I want that sort, because it's the sort I'm used to. So I should draw this one, but not that one, and this one, and this one, and this is already a nightmare. It's really hard to keep track of all of these lines. So maybe I need a different method. First time live, says Anonymous. Hello, good to see you. I would like suggestions from audience. I think I'll put chat back on the screen and everything. Suggestions from the audience. Oh, so I didn't connect or adjacent ones because, well, I'd already drawn this circle and I thought, oh, okay, maybe I should draw in a straight line here. You're right. I thought that would look a bit messy. I suppose I've now given up on my picture. I think my picture is too messy. And there's some like combinatorics or something in there. We could use letters, couldn't we? We could name things. I quite like that as a suggestion. We could give the points names: A, B, C, D, E, F, G, H. And then what do we want? Well, it's tricky, isn't it? I want 2 of those, but not AE, and not BF, not CG, and not DH. So that gives me this idea that if I'm counting all the lines to do part 1, if I'm counting all the lines, then I think I want to get, yeah, so 8 choose 2 minus 4 seems like a, 8 choose 2 minus 4 seems like a good answer. It says explain your answer. We've done a bit of that out loud. Talk about all the lines you might have got, minus the ones that aren't there. Other approaches, right? Other approaches. So someone in chat says, nice. You can see 8 choose 2 minus 4. Yeah, so later A, B, and C turn up, but you know we can maybe get away with A, B, and C a little bit now. Was it technically directly opposite to all points? I don't think so. Clue, if you believe that E is directly opposite to all of the points, then there are no lines, which can't really be the answer, can it? It'd be 0 for, I think, all of this. Yeah, which is the number 24, I think, right? H choose 2 is 8 times 7 divided by 2, 28 minus 4 is 24. Final answer. Hello, I'm not sure I understand what this is. Is this part of the MAT livestream? Yes, this is a bonus episode. Let me show you very, very quickly. We do this every year. I agree it's confusing, but even though the MAT has now happened, and we did all of our live streams, and that finished in October, and we said goodbye, I couldn't resist coming back to talk about MAT 2025. And what's worse, I'm coming back again in a couple of weeks to talk about interview questions. You know, I also run another show called the Oxford Online Maths Club, which comes back in January, where we talk about just other sorts of maths. I've been live almost every Thursday for the last 5 years. Anyway, yeah, that's what this is, just continuing maths on YouTube. And I shouldn't apologise because I'm not sorry. Right, 8 times 6 divided by 2, I like that a lot as well. Or 8 times 6 divided by 2 is a good answer, and I think here they're thinking about there are 8 points, so A to H, and for each one there are 6 things to connect to, but oops, so you could go A to, and then you could go A to B, A to C, A to D, but not E, F, G, H, 6 things it could connect to, but this is going to double count because I'll see A, B on my list, and I'll also see B, A, so this is a 2 for double counting. Okay, nice, either way, good. Okay, right. Yeah, 1357 in chat has just like moved on, which I think fair enough. Question then tells us about a 3-star, which is a weird name for a triangle, right? Because there are 3 distinct points, each pair connected by a straight line segment. That is a triangle, but hey, whatever. How many triangles are there in this image? I really do not recommend trying to draw all of them or count all of them, partly because there's quite a few, and partly because, well, it says explain. And your explanation cannot be something like, trust me, I've drawn loads. I've drawn so many, and that's probably all of them. That's not going to do. So this is the key here is to try and describe it, or describe what you're doing systematically, and you're almost forced to do that by the fact that you can't draw the diagram in the box. And of course we knew when we designed the question that you would probably want to draw the diagram on the scrappy whiteboard paper stuff, but the fact that you can't draw that in the text box means that that's helping you to think about this another way, to have some other idea. So I think actually probably the use of text boxes for this, probably, if you just set this question on paper, there would probably be some candidates who just drew like a complicated thing and wrote loads of numbers on it and went, 23? Is it 23? Don't do that. Yeah, so something about A choose 3 is a good start, right? Because A choose 3 is a good start because we should choose 3 points to be the corners of our checks notes 3-star. But of course, some of the lines are not actually there. So AE is not there. So we could do H choose 3 minus something. And you can work out the something, because of course you can reason about how that would be all the triangles. But some of these include one of the long diagonals. None of the triples, like ABC, none of those triples contain 2 long diagonals. Because you've got to think about it a little bit, I suppose. But if you can take 2 long diagonals, that's either the same long diagonal twice, or it's 2 different long diagonals. But that would use 4 points. So when you name 3 points, they can't contain 2 long diagonals. 2 of these opposite pairs. 3 is less than 4, something like that. So minus, and then you've got to remove the bad ones, and then some reasoning for the bad ones. Eric in chat says 6 times 4. That seems good to me, I think. I can't remember how big H choose 3 is. I've got to work it out now, haven't I? 8 times 7 times 6 divided by 6 is 56. So I think Eric is going to subtract 24 and get down to 32, which seems right. Why is it why is it 24 to subtract? So 6 times 4, I guess because Eric's thinking maybe about the four long diagonals. Each of those you could make into a triangle by adding in one of the 6 other points. And those are the triangles that are not there, because that long diagonal is not there. So I like that. Yep, you could do something like that. Yeah, it's 4 diagonals and 6 back ones. Thank you, Eric. There we go. And someone says 5 plus 4 plus 3 plus 2 plus 1, because if you take one side, e.g. EF, to be the base, then there are 5 possible triangles, then take the next side. But there's also a triangle EBF, which doesn't involve any sides at all. I don't mean BF, I mean EBH. Which is a triangle in there. It's quite hard to find because it doesn't involve any of the outside sides. It just involves these like longer sides, but no long diagonals across the middle. Anyway. It does turn out to be minus the 24 in part 1, but I think it's a different 24. There's a hill to die on. Yeah, Matt in 10 minutes has got a bit... Matt in 10 minutes was fun while it lasted, I think. People also found that annoying. I definitely wouldn't have watched Matt in 10 minutes. This is a thing we used to do where, about 2019, we did this, like... I think it was my first YouTube video on Matt, which is like, ha 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 ha, here's me reading out all of the answers at 1,000,000 miles an hour. It's sort of a stupid idea. But it got 250,000 views, including some very, very confused people. So I guess Matt in 10 minutes might be the reason why I'm allowed to do Matt Livestream. Like, that was weirdly popular. Shall we do it properly? Oh well. Right. Okay, good. So other arguments here. And then we find out in part 3 why the question says 3 star is because they want to talk about n star as well. So instead of 3 stars, talk about n star, which is a collection of n distinct points with each pair connected by a straight line segment. So something like this. People who, yeah, it was a little bit like, we did it again in 2020 and it had to be like, hi everyone struggling in the pandemic, just be clear, I have unfair advantage that I've thought about these questions before, I'm not actually doing them live in 10 minutes. Ooh, it wasn't as fun. Right, other than stupid YouTube videos I've made. We're down here thinking about 4 stars. 4 star is a collection of 4 distinct points with each pair connected. So can you find any of these in the diagram? And the key thing here is, I think, because each pair is connected, you can't have any pair of these be an opposite pair. That if you put A in your 4 star, then you can't have E. If you put B in your 4 star, then you can put F. And also if you put F in your 4 star, then you can't put B because they're not connected. And you need so many connections inside a 4 star. You need everything to be connected, every pair. So thinking about it like that, how are we going to do this? So how are we going to do this 4 stars? We're going to work up, I suppose, 4, 5, 6, 7, 8. So this is like, I suppose, the logical progression from lines to triangles to, do you know what this shape is? If I colour in one of the faces? It's a tetrahedron? Triangle-based pyramid? I mean, it's flat, it's been flattened, but it's a tetrahedron. Yeah. I'm not going to comment on multiple choice questions at all, I'm really sorry. I know they're interesting. This year and last year, some of them I would really like to talk about, but we're not talking about multiple choice questions this year or last year. So. Last year was the heartbreaker because I thought maybe we would be able to anyway. Right, okay, we're doing this, or we're just sort of doing other stuff? Oh no, Arav doing this. Something with h use 4. Something with h use 4 and some elimination. I like this. We've got h use 3 minus something in here. Let's write h use 4 minus something else. I am not commenting on how many marks you get for h use 4 minus something else. But it's a start, isn't it? You kind of want to choose 4, but then it's going to be so hard to count these. So I think a way to think about this is you want A or E for one of these corners. Not, you can't have both. B or F, C or G, and then D or H. yeah, so 2 to the 4 language. So 2 to the 4 because you get a binary choice about whether you put in A or E, and you have to have one of them because there's only 4 sets of opposite pairs: the AE pair, the BF pair, the CG pair, and the DH pair. I'm trying my hardest with the letters. That was somebody else's suggestion at the start. Yes. Is this 4 times harder? No, I don't think so, because there's this idea that you can use where you think about the opposite pairs and you choose just one end of that opposite pair or the other. And then, I know it looks like loads more work, but for n greater than 4, there are no n stars. Because if you try and pick 5 points with every pair connected, then 2 of those will come from the same opposite pair. So you can't have 5 things without having 2 that are opposite. Right. Okay. Good. The question then moves on to a different diagram. So I want to quickly tell you about this diagram. I put it in the thumbnail as well. Before we, move on. Right. So 4, and then there's 5, 6, 7, 8. Let's do a sort of sincere attempt to draw it. So you've got these kind of opposite lines. You've got this octagon around the outside, and then you have these kind of parallel pairs that skip 2. Maybe I should do ones that skip 1 as well, but so you have these that skip 2, and they come in these varieties like this and like that. That gives you a nice octagon in the middle. And then you have the ones that skip 1. So that's this, 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 and that, which is a pair of squares, I suppose. And that means that everything has got 6 points coming out of it. I mentioned something about squashing a tetrahedron. This graph is a squashed down version of a 4-dimensional object, which I'm not expecting you to have seen, but there's this 4-dimensional object called a 16 cell, which is a bit like an octahedron in 4 dimensions. You can build one of these if you live in 4 dimensions by putting points on the x-axis at 1 and -1, on the y-axis at 1 and -1, on the z-axis at 1 and -1, and then on your 4th axis at 1 and -1. And if you put points at those 8 places and join up the ones that are √2 apart, whatever that means, then you get this shape. So in 3D, that's a recipe for an octahedron. In 4D, that's a recipe for this thing, or at least this series of connections. And what you've done in this question is you've counted how many edges it's got, you've counted how many faces it's got, and you've counted how many volumes it's got, which is a thing that 4-dimensional shapes do. You are 1 step away from calculating its Euler characteristic, but not that important. In case it hasn't become clear, this is a question that I was involved in, which is why I like its background material, right? But it's come from a place of high-dimensional Platonic solids. It's come from a place of Euler characteristic and thinking about counting simplices. Anyway, none of that's important, of course, when you're actually doing it. When you're actually doing it, you're trying to do combinatorics. In terms of the fact that it's combinatorics, if you generalize that nicely, you can get to a result to say something important about the generalization of that shape to n dimensions. It's also called the party graph. The party graph works like this. You have 4 couples who have arrived to a party, and here we go. So different colours, and I'm placing them opposite each other. Look, 4 couples have arrived to a party, and when you go to a party with your partner, it's rude to talk to your partner. So the first thing you did was you counted how many conversations there are where the people are not talking to their own partner, the person they came with. And then the thing you're counting is how many 3-person conversations you can have for a 3-star. How many 3-person conversations can you have where nobody's talking to their partner as part of that conversation, and then 4-person conversations. So there's this version which is called the party graph, which does the same thing. Right, good. I've now had all of the opinions in chat, which is, I'm glad I didn't do this question. I'm sad I didn't do this question. This looks easy, this looks hard, this looks, right. I'm just going to observe that we've had, I think, all possible combinations of opinion. I'm going to move on in a moment, but yeah, so I'm writing n-choose, like n-choose r notation in here, and I'm thinking about choosing. You could just do some multiplication, and you could also just do some counting. So some people told us there's a pattern as you read around for the number of lines. You see 6 lines coming out of the first one, but then from the second one you've already seen one of them, so you see 5, and then from the second one you've already seen a couple of them, so you see 4, and then 3, and then 3 again, and then 2, and then 1, I think, which gives you 11 plus 10 plus 3, which is, I've gone too many, haven't I? Oh no, that's 24, good. So you can do some sort of sum for counting carefully on the way around. That's allowed. For the other parts of this question, there's a new diagram with ABC, collections of points with loads of lines like this. And you're asked how many triangles there are in this picture, how many 3-stars there are, and you have to justify your answer. So people worked out that you should probably have a point in A, a point in B, a point in C, perhaps, because that's where the connections are. And then justifying that that's all of the triangles, that you haven't missed any, is what the question is getting at. And then finally the question asks you to go on a journey around these points and to talk about how long that journey might be. And I think the answer is that it's anything from 4 to 12, and you can just demonstrate them. You can just go for it. It asks you to do a thing. In fact, this thing is, in some sense, always possible until you get to 12 when you run out of points, and it's just about route planning it all the way around. Right. I don't think we've had I wish I'd taken this one because it looks hard. We haven't had that. You're correct. We have not had the combination I wish I'd taken this one because it looks hard. Some people just built different like that, right? Okay. I think that's what I want to say about 26x. Like, there's some stuff to do. It's related to a 4-dimensional shape, but obviously, look, I don't want letters saying it's unfair because some people are naturally from 4 dimensions. Or that's no. I actually don't think that knowing about 4-dimensional geometry gives you very much help with this at all, because you still have to do the combinations. You still have to write down an explanation. So I don't know. Right, shall we have a look at 26y? Let's swap, I think. Let's swap. Yeah. Good. Okay. Like the Harry Potter series. Is this because I'm wearing glasses? So I must be a bit like Harry Potter, right? That's how that works. I've had that before. Right. Okay. Right. 26y. So it's another question. This one's about linear polynomials. Here we are. Immediately the duality. There it is. Straight away. Thank you, chat, for demonstrating. I'm sorry, chat, but that's just perfect, I'm afraid. It was fun and it was tedious. It was tedious and it was fun. It was the best of times. It was the worst of times. Right, okay. 26y, let's go. Given 2 linear polynomials, we define an operation dot as follows. To calculate f dot g, we multiply the polynomials as normal, but we ignore any x squared terms. So for example, to multiply these polynomials, we would do it as normal, where you would get 3, take away 11x plus 10x squared, but then we ignore the 10x squared term. Haha, so we get 3 minus 11x. The question wants us to do this in general, and then to go from there. So off we go. Timings, right, okay. If you have just seen this question for the first time, try and keep up. Let's go. I've got 25 minutes. I'm going to try and do all of them. Here we go. So coefficients of this is actually quite relaxing, right? Because you do the normal polynomial stuff. So BC plus ADX. But you stop early. You don't have to write down the x squared term. So that's quite fun, I think. I don't have to write x squared because I'm ignoring the x squared term. And then it says explain why. People did different things for this. What I'll do here is I'm going to calculate this. So to calculate this, that's c plus dx, a plus bx, and if you just go for it, then this is ca plus, and then what would that be, dA plus cbx. It's the same. It gives you the same terms. We're ignoring the same x squared term for both of these. Okay, things work out. Then we're asked to do some division because we're asked to find a linear polynomial such that polynomial times 1 plus 2x is 3 plus 4x, which I don't think I've thought about this, but can you do that for normal polynomials? I don't think you can. Maybe you can. No, you definitely can't. Yes. No, you definitely can't. You definitely can't. You can't do that for normal papers. Yeah. Okay. Is there a 6-7 meme somewhere? I can't remember when 6-7 caught on. I mean, we have 26 and we have 27. So, like, comparing those with other 20s, if you were desperate to find the number 6-7, we had a good one in 2020, but that was a few years ahead. I can see the number 6 coming up later. I'm aware that people are fans of a particular pair of numbers. Okay, right. So we're asked to find a linear polynomial here. We know how to multiply though, right? So we want AC is 3, and we want BC plus AD to be 4. Oh, wait a minute, and we know C is 2. So 2A, whoops. We know C. We know C and we know D. So I think we want, think about the constant coefficient. We want A to be 3, and then it's a matter of getting the coefficient B correct. Doing some linear algebra, not on the screen, but doing some linear algebra. I've got it written down over here because I did it before the stream. 3 minus 2x works. Recreational math is unpleasant. That is a mood. That's a real mood. It's called recreational. It's supposed to be fun. Is it plus or minus? Oh, I've got minus. I'm pretty sure I want a minus, right? Because then I want 6 minus 2. Anyway. A student is back. I can't remember when we last saw the student. It might have been MAT 2020. MAT 2020, the student, the question said, a student says, and they had 1 success and 1 failure in MAT 2020, like the person in the question who's making a claim. Here, they make a claim, and the student's claim is not correct. It's not that hard to find a counterexample. What we need is 2 functions with sort of a minus sign on x, so 2 decreasing functions, maybe. And what I need to make happen is I need the coefficient of x in this, so this will be ab minus a plus b x. If I can just make a plus b negative, then I'm good. So if this is like minus 1 minus x times minus 2 minus x or something. Those are both decreasing functions, but once you dot multiply them using this new thing, then you get x and you get 2x. So you get 3x, which is a bit weird, but there you go. 2x and 3x. Increasing. I mean, yes. Yeah. Only allowed to see sunlight when James forces him to give him math questions. You there, make some errors, make some blunders, so that I can then quiz everyone else on your blunders. You're wrong again, hooray! That's the scene? That's the scene. That's what we've got. Right. Maybe they're not a math student. Right, okay. I thought naming them again. I mean, in my head, all of the blunders are by Charlie, the student from, well, not a student, but there's a student called, there's a character called Charlie who is bad at cutting cake in an intermediate year, and in the past was like writing numbers on people's foreheads and did some logic games at one point. I think they broke a vase. There's like a long-standing Alice, Bob, Charlie sort of world. Right, okay. We'll fill in the gap now, isn't it, for who you think might believe the product of these. Yeah, from the old logic questions. But then Charlie stuck around for a bit and did some guest appearances in questions sometimes. So I thought this would be Charlie. Anyway, never mind. Now, it's weird, I think, if the question is just like, here's Charlie. Charlie's maybe wrong. Like, who's Charlie, right? Out of nowhere. 26x, 3n greater than 4. You have to stop at 12 because you've only got 12 points and the points have to be distinct in an end loop. Right, okay. So there's a proof here to prove that this is associative. It doesn't say associative, but to prove that f dot g and then dot h is the same thing as g dot h and then dotted on the left with f. I would just check this, I think. So I would give them names like a plus bx, c plus dx, and then I'm going to skip e and f. I'm going to go for p plus qx, and I would just do it and multiply things out. Here, there was maybe a problem where if people just said it's associative, then that's the question. So it's not just looking for people to do things. I can't make think about this stream as other people saying they're cooked. Right, okay. Oh, the first part. Oh, I forgot the first part. No, I don't know. I mean, it's a bit of typing, right? It's a bit of typing. It could be worse. Could be a humanities student where they get like essays and things, right? We have polynomials. I mean, you can ignore a lot of terms along the way. So there's a lot of ignoring. Okay. Charlie from the Charlie brackets 2021 as made popular on previously featured on math questions. Part 4 asks us to do a big multiplication. There is an increasing sequence 1, 2, 3, 4 up to 2n here, where I guess part of me is sort of hoping that people spot the kind of general pattern here that if you have this, then with a dot, you get 1 plus a plus b x, and then you throw away the x squared term. So it just adds them together. So the question is just asking us to add together 1, 2, 3 up to 2n, and it's 2n because I think that makes the answer look slightly nicer, but not a lot nicer. Okay, right, good, yes. Yeah, I don't know. I mean, I might talk about the maths behind this one or not, I don't know. 5 and 6 are the interesting bit, I think, for this. There are interesting possibilities where you can dot things together and get 0. So if you were playing along just using normal polynomials, then what would you get? If you were just doing normal polynomial multiplication, then, well, this bit's impossible because you can't solve that equation with a polynomial. And then further down, this bit's really hard because the degree of this polynomial is enormous. So you have many, many, many coefficients. The clickbait YouTube thumbnail perhaps could be find and then this big product. So you think you have to multiply it all out, but that's clickbait because we're throwing away x squared terms every time we do a dot. Throwing away x squared, which means we never get any x cubed terms because we only ever get x. We never see x squared and certainly not x cubed. Right, okay. So we already have an expression for f dotted with g. If I'm calling these a plus bx and c plus dx, then the expression is ac plus, and then it's ad plus bc, ad plus bcx, which is, okay, anyway. So could this be 0? And I suppose that means 0 plus 0x, right? Another way of writing 0. Question mark. And I suppose in order for that to be 0, we would need either A equals 0 or C equals 0, then, so A equals 0. If A is 0, then I would need also, we need, and in this case we need BC to be 0. So this leads us to different cases. We could have B being 0, or we could have C being 0. And over here, we would also, we need, in this case, if I've decided that C is 0 for the constant, while looking over here, I would need AB to be 0, which splits into two cases, A equals 0 and D equals 0. And a little bit, I suppose, this is a test of being careful about cases, because there is a non-trivial case in here. There's one, so either A equals 0 and B equals 0, that's like the left branch of my left branch, or, and quickly interpret this one, if A is 0 and B is 0, then f is 0. The function f is just 0. Or I can have C is 0 and A is 0. No, yeah, no, sorry, C is 0, so reading down my left branch and then choosing the right branch. So that one's interesting. Or there's a third case, reading down this branch. So this one gives me C is 0 and A is 0. But going down that last right of the right branch gives me C equals 0 and D equals 0, which is kind of a boring case of just G could be 0. If G is always 0, then it doesn't matter what you dot it with, you're going to get 0. But this middle case is interesting, where the constant coefficients of each polynomial are 0, but the functions themselves are non-zero. So we have f is equal to, I suppose, in my notation, bx, and g is equal to dx for some like some real values b and d. Yes. Is that the answer? That does look like an answer, doesn't it, for part 4? Yeah. What have I got? 2n plus 1. Have I got fewer factors of? I think I've got fewer factors of 2. Have you divided by 2 on your sum? Okay. So it's all 3 cases. Maybe one of the polynomials is 0, or maybe you had like 3x and 5x, and when you multiplied them, you got a thing you could just ignore. You ignored everything because it was the only term you got. There's some maths there to work out that that's all of the cases. There's a request to go back to I didn't give you an answer for this, did I? So after adding all of these things together, you get 1 plus, and then adding the numbers from 1 to 2n is 2n plus 1 over 2. Oh, not that much over 2, that much over 2. That many x. Which I suppose is n times 2n plus 1. Hooray. Counterexample for 2. So I've got this weird counterexample down here. Minus 1 minus x times dot with minus 2 minus x is 2 plus 3x plus x squared. These are both decreasing functions. What have I done? Yeah, what have I done? I don't understand my counterexample either. Thank you, Diego. What have I done? Yeah, I've done it completely wrong, haven't I? What was my counterexample? Okay, right, sorry. I'm supposed to do, I've misread it. It's supposed to be strictly increasing functions. Thank you. Did everyone spot this? Yeah, f and g aren't strictly increasing in my example. Whoops. I knew when I wrote out the examples that I'd gone wrong. Okay. What if they're a plus x and b plus x? Then the product on the dot would be ab plus a plus bx. Rewind. But all I need to do is to make a plus b negative. If I make a plus b negative, for example, minus 1 plus x dot minus 2 plus x, that's 2 minus 3x. Aha, brilliant. We've got 2 strictly increasing linear functions, but the dot is not a strictly increasing linear function. It's a decreasing linear function. Yeah, mine was wrong, I fixed it. To do a counterexample, I was supposed to do something where f and g are both strictly increasing, but this is not. Right, okay. Good. Okay. Right. Okay. In the last part, which I think I'll just talk about out loud, maybe because I've already made a mess everywhere on the page. In the last part, there are different cases to think about, depending on, well, which of the cases we were in for the previous part. One way to think about this, let's just erase some stuff because it's got a bit messy. One way to think about this last part, where we have f.g.h equals 0, is, well, we could remember that this means f.g then .h. So if you squint, you've got two things there dotted together to give 0, which is the previous part of the question. So we already know some possibilities about that. We need to look a bit further because, well, some of the cases are interesting, right? So there's two easy ones, which is maybe h is 0. That would cause all of these to be true, good. And maybe f.g is 0, which is literally case 1. But there's this interesting case where h is a constant multiple of x, and so is f.g, and we should go and think about that case. So there's an extra step of work to say, well, what if f.g is a constant times x? And you can go into that case and say, well, then the constant on that polynomial, the constant term, is 0. That's the punchline of the previous part. The constant term is 0, which means that either f or g has 0 as its constant coefficient. And then take that one. So now we found another one of these polynomials, where another one of that type of polynomial where it has 0 constant coefficient. So crucially, when you have this product, it's sort of obvious that one of them must have 0 as its constant coefficient, because the constant coefficient at the end is going to be the product of all three of those. You've already done some working out in a previous part of this question to work out the general formula. It's kind of obvious that one of them has got 0, but there's a possibility, that's a relevant possibility because it might matter for one of these, that two of them have constant coefficient 0. And there's a part of the proof where you kind of say that could happen. Can A, B, C, D, E, F, G, H be an 8 star? No, because in an 8 star, every pair are connected. Not just, that can be an 8, that's an 8 loop, but not an 8 star in the language of question 26x. Got it? Hello, anonymous person. Right, good. Okay. There's a last part here to give examples of polynomials for which that statement is true and the other two statements are false, to show that you can't do better. It's not the case that this one always implies that fact, and it's not the case that it always implies that fact, or even that it implies that fact. It could be one but not the other two. So I'm trying to find examples, and that's phrased so that you can't just say f is 0, because that would get two of them. No, not stupid. There you go. How would you justify that one to be 0 in words? I would write out some more stuff about coefficients, right? I would give things names. So I think in my rough working out over here, I've got, I don't really expect people to write like this, I suppose, but .gx. Oh, I've used a kind of star. I think the question on the Pearson VUE system said you can type an asterisk or a full stop for that. I've got an asterisk on this bit of paper. Then I can talk about the coefficients of big F, because I have this .h equals 0, like in V. And now I'm going to talk about the coefficients of those polynomials. I'm going to give them names as well, and work through the steps. At some point in my working out, I've got, so one possibility, not the only case, but one possibility is that f of x dot gx is equal to, and then in my notes it's bx for some b. So then I've given these coefficients names as well to split that further, to look further into f and g. That's not what I want. I wanted to say it was 0. Rat, it's not always 0. Sometimes it's bx. Brr. I should look further. So constant coefficients here of like, I think I've already used a at this point, so I'm running out of letters, but you know, like p plus q, r plus s x or something. So p r equals 0 or something like that. Right, keep working. Good. When am I going to do 27x? I think I'm going to do 27x within the next 5 minutes. I think it's going all right. Can we give an example where 1 is true and not 2 or 3, and then use some sort of argument? I think. I don't think that's commutativity. I don't think that's commutativity really. I think you're just. Well, actually, I suppose you've proved commutativity in part 1, so go for it if you want. But yes, once you found an example, there's some symmetry here to switch F, G, and H. So you could say, look, rotate it around, do the other ones. I think that's right. Good. Okay, so very briefly, somebody mentioned dual numbers in chat. I'm surprised you've heard of dual numbers. They also mentioned it in the context of not realizing this was dual numbers until afterwards, which is good, I think, for you. But you still have to do so many calculations, even if you've worked out which algebraic structure this is. This is a thing, sort of, a bit. This structure where you have a pair of numbers and another pair of numbers, and instead of doing your normal dot product, you say, I want to multiply these and get AC, AD plus BC as a pair of numbers. That's not dot product or anything like that, if you've seen dot product. This gives you a space that is not very well behaved. It has non-zero things that multiply to give 0, which is not very nice. So this is almost an exercise to work out that this was not really a very good idea, that you get a system that doesn't behave very well at all. They're called zero divisors, these things that you have 0.1.02 is equal to we have this pair that multiply to give 0, which means it's not an integral domain. Have people heard of dual numbers? I had not heard of dual numbers when I came up with the idea for this question. So I learned about them out along the way. There we go. The concept for this question initially in my head was, can I do anything with polynomials? We can't type x squared. I would like to do something with polynomials, but I would not like to have x squared terms. And then I found out that that's a real thing. Some people did type x squared a little bit in order to tell us what they were ignoring, but they found ways to do that in words or whatever. Math Society. Cool. Good. Okay. Big grin. Okay. So 3 possibilities at the end. Right. Okay. Almost 6 o'clock. Reminder: if you've been looking at a screen for the last hour, remember to look away from the screen occasionally. Remember to blink. Studies show that people don't blink as often as they usually do when they're looking at screens. I'm going to drink some water. An anonymous person who's done a course in linear algebra sent a chat, and they have capital R for real numbers, square bracket x, close square bracket, that means polynomials, so it's a way of saying polynomials with real coefficients, / that means quotient, it means ignoring, and then in angle brackets, that means anything that's a multiple of, and I've got x squared inside the angle brackets. So that's a concise notation: real coefficient polynomials ignoring multiples of x squared. What that notation means in chat. Thanks for putting algebra anonymous person. Could you do it without choosing? Yeah. I tried to analyse it. So, well, I think we're on a 2-minute break in between questions for me to reduce eye strain and to talk about what other ways of doing things. Yeah. So people do this kind of counting argument going round. There's a thing in here where instead of doing h is 4 minus something else, you do 2 to the power of 4, which is 16. You just sort of say, you have these choices. You can make independent choices, but then you're done. That's what you've got. Right, okay. Long question taking account of choice questions. Yes, well, how about them? I think I want to say that Oxford has quite a lot of control over the MAT, including we do know what we know what we did. That sounds really ominous, doesn't it? But we know what we did. Good. Okay. Right. Yeah, I'm being told off for not being into maths enough. I did go and find out about them. I just didn't know they were called dual numbers, I suppose. Right, it's nice sets time, I think. Nice sets. Here we are. The original idea for this question came from the computer science department. Many people asked me in the lead up to MAT whether computer science, like, oh, there's no computer science questions, or maybe people thought there are computer science questions because there aren't any special computer science questions. And all along we've had question 5 in the old days was usually written by computer science department, and I've had questions like this written by the computer science department, but not involving any computers. So sort of I had to answer questions about computer science questions while knowing that there's essentially no difference between them. But never mind, here we are. Right, okay. What are we up to? We're going to do this now, I think. Big blink. Here we go. 27x. In this question, we will write 1, 2, 4, 5 in curly brackets to mean the set containing numbers 1, 2, 4, and 5. The order of the numbers in a set doesn't matter. Numbers in a set cannot be repeated. All the sets in this question contain whole numbers, positive or 0 or negative. We say a set of whole numbers is nice. There is the word. And that is a fairly, we say it's nice if there is a number t such that the numbers in the set can be paired together so that each pair adds up to t. If such a number t exists, we will call t a target for that set. For example, this set is nice because you can pair them up 1 plus 6 and 2 plus 5. And you get 7 both times, so we can take the target to be 7 and then pair the elements up. This set is not nice, and then the question text says quite vaguely there is no such number, which, it's not obvious, but there you go. In the second half of this question, we will imagine that each whole number is coloured either red or green, and we will look for nice sets with all numbers the same colour. That's something we're going to search for later on. Okay, off we go then. Here's quite a large set, and we're asked whether it's nice or not. I'm going to scroll here so that you can still see this definition of what it means to be a nice set. And here's a set. We're asked whether it's nice, and we're asked to justify our answer. There are 2 marks. People in chat say, no, please could people in chat justify your answer, and say, why not? Why is that set not nice? You're correct, it's not nice. A student says, I think this set is nice. You say, no, Charlie. I know it's you. You're wrong again. Oh dear. Can't shake the student who's wrong sometimes. Right, okay, how are we doing? Yeah, you've got to pair them up. You've got to pair them. So the set can have more than 2 numbers in it, right? Yeah. It's a bit of reasoning to explain why you want to pair the first and last. Yeah. I think the set has been constructed so that the total is quite a nice number, just in case you're thinking, but if it has some target, maybe we could add all the numbers together to try and find out what that target is. There are, 8 numbers in there? So hopefully if I add them all up, then I'll get all 4 pairs. I think the total is 48. So I sort of think, yeah, can you choose target t? So I think a full, comprehensive, I have no further questions kind of answer would tell me, on the one hand, why t has to be 12, and also t can't be 12. Maybe we have further questions when we see those 2 statements, but therefore there's no target. A reason for why t has to be 12, why is it 12 in particular that we're looking at, might be if you add all of them, you get 48. But a different reason might be that if you look at the smallest, well, the smallest number always has to pair with the largest number for a nice set. That's not obvious. If you think about it, there isn't a better alternative, because if you pair it with not the largest, then what on earth are you going to pair with the largest number? Something bigger than the smallest number, I suppose, like this, but that's definitely going to be a larger pair. So not obvious, but if you mess around with it, nice sets a little bit, you realise you kind of always want to pair. No, you absolutely always want to pair the smallest number with the largest number. Okay, so some sort of argument that t has to be 12, because I'm going to pair the smallest with the largest. Or I've thought about the whole set and I've divided by 4. Maximum minimum value of the pairings. Yeah, one has to be paired with that one. And then what? Well, that's a pair set, so now we have this the remaining numbers in there, still got to pair them up. You can make some progress. 2 would have to be paired with 10. That's the next step. And again, I'm saying have to because I'm trying to convince you that this is a direct consequence. I'm not just doing a bad job of pairing them up. There's no way to pair them up to get 12 each time, because then what am I going to pair 4 with? Or I suppose maybe more directly, as soon as you've decided that the target has to be 12, you have made the 4 sad. And also 5, 6, and 9 in the middle there. So like they're kind of I think as a mathematician reading this, I would say, you know, I want to see to do this absolutely. It's sort of a bit 12 is kind of the number jumping out of the page at me, but there isn't a 12 printed there, so I should probably justify why I'm talking about 12 or what's 12ish about this. This looks a lot more fun than I expected. I tried my earlier statement about recreational maths. We did it. We did it. I don't even know if I describe it as recreational maths. I sort of think it might be a little bit close to Ramsey theory. It's not really Ramsey theory, but there's this flavour of colouring all the integers and looking for patterns within that. It's a thing. It's a thing that people do non-recreationally. Anyway, right, okay. What should we do for part 2, where it says, prove that for any nice set of 6 numbers, the total of those 6 numbers must be a multiple of 3. Not 6, multiple of 3. I mean, if you can prove it's a multiple of 6, go for it, but that's not true, so don't try too hard. Fun or not, I think part 2 here is about having an idea. Because, well, you could try and work out a formula for all possible nice sets of 6 numbers and then check. That seems hard, unless your formula is extremely general and sort of identifies the correct idea anyway. The numbers are in pairs, right? Some letters in chat. And I think it's the thing, I was talking about the total being 48 a moment ago. So if you're following that, then the idea is that the total includes all 3 pairs. Each of which sums to t. So you have, in an ideal world, a nice set of 6 numbers, you have 3 pairs of numbers that each sums to t. So if you add the total, you'll get 3t. And 3t is definitely a multiple of 3. It's just 3t when you add them up. Good, you get a mark. Apparently for this part of the question, it says 1 mark for 3. Nice, okay. Now there's a 6 mark part of the question for talking about infinite sets of whole numbers. Infinite sets are tricky to think about, especially the idea that we're pairing up numbers from the infinite set. But I mean, we're not allowed to pair any particular number with the infinity-ness of the sets. We can't sort of take all of the positive whole numbers and pair one with the distance, and then pair 2 with slightly less than the distance. You can't pair things with infinity, because infinity isn't a whole number. Right, okay. Got some guesses in chat. Yeah, okay. So this might be one of the most open-ended questions we've done on math in recent years, in the sense that there are many correct answers for this. Many incorrect answers as well, but there's lots of things you could do. I'm really glad that it's marked by a team of graduate students who could analyse arguments about sets, rather than, maybe in a different world, I have to write a mark scheme where I list all possible sets of whole numbers, and that's actually impossible because you can't list all of the sets of whole numbers because they're unlistable. There's too many. No, don't. Oh, well, you can leave if you like, but infinity is not a whole number, so I'm probably going to be resistant to the idea of pairing 1 with infinity and 2 with infinity. Reals, okay, reals between 1 and 2. Oh my goodness. Pair 1 between 1 and 2. Pair. There's something there, isn't there? Okay, right. Is it whole numbers? Whole numbers question? Anyway, never mind. Okay. People are thinking about numbers in chat. Here we go. The example of an infinite set is the set of all positive whole numbers. So we should think about those, right? Is it possible to pair these up? Is it possible to pair these up so that you always get the same sum? And people generally said, no, you can't pair these up, right? Not possible in some sense. It's not nice. There's no way to pair these up because whatever your target is, then the positive whole numbers keep going. So whatever your target is, if your target is like 1,000,000 or something like that, you've made a really large target, that's great. You have to pair 1,000,001 with something. And -1's not in your set. So whatever your target is, pairing t plus 1 with you can't pair it with -1, that's not there. T plus 10, you're also in trouble. Okay, so that actually works as an example with no. So what do you pair t with is like my justification. I suppose t plus 1 or t plus 10 or something. Exactly one target. Well, the key here is maybe to pick something with a bit of symmetry to it, but let's be careful because if you go for all of the whole numbers like this, then this has a target of 0 because you compare. Oh no, it doesn't, does it? This has a target of 1 because you compare. Oh, this has gone a bit weird, hasn't it? It doesn't have a target of 0 because what am I going to pair 0 with? It's got a target of 1 because I compare like this. But it maybe doesn't have that nice symmetric target of 0. If you remove 0 from that set, so if you take out the 0, then if you take out 0, then you get a set that only has one target. That target is 0 in the middle. You pair everything on the outside. And if you try to hit a different target, then what are you going to pair with t? Because you've taken out 0 from the counting numbers. Yeah, you got positive and negative numbers. Chat is sad about negative numbers right now. Whole numbers? Oh no. Yeah, you do probably need some negative numbers. If you're stuck on whole numbers, you do probably need to use some negative numbers. Otherwise, I think the argument that we just had about the infinite set getting really large without getting very negative. Yeah. So if I have 0 in my set, then I can't have 0 as the target because I would have to pair 0 with itself. But there's another solution where if you remove 0 from your set, then aha! Now I can pair them up to make 0 every time. 1 with -1, 2 with -2, 3 with -3, and so on. And I can't make anything else. Because if I try and make a different target, well, that's a number in my set. So I would need to pair it with 0, but I removed 0 from the set. There's all some, not circular logic, but there's some sort of quite close arguments about t and 0. Right, you can't repeat numbers here. Multiples of 10 not including 0, that only has 0 as a target. You can take that picture missing 0 and you can scale it. You can remove some other stuff as well if you like. So you can do something like square numbers and negative the square numbers, and then the only way to pair them up is the obvious way. And then there's a claim, what happens if we have the integers with 0 in? So we put 0 back again. What sort of targets do we get? and there are infinitely many possible targets, more than one target. We can make one by pairing like this, or we can make three. Yeah, sorry, we can make three by pairing like this. I can't actually make the target 2, because if I want to make the target 2, what do I pair 1 with? If I'm trying to make target 2. Well, 1 plus 1 is 2. Welcome to the Oxford MAT Livestream. And that's a problem, because I'm not allowed to pair a number with itself. So solutions to that: if I really want the target to be 2, I could remove 1 from my set and say, no, I didn't mean that, I meant not 1, no 1 in this set. Or I could look for a different target. Cool, right, yeah, so the target can't be even for the integers, which is amazing. Whole numbers, I think negative whole numbers is a thing. Is this a thing? Oh no. Yeah. Okay, right. Good, right, let's do the colouring part of the question. We got some time. Oh, okay. So there's other examples you can use. I've only talked about a couple of examples there. I don't want anyone to watch this and think, James didn't talk about my example of numbers and sets, because, as I say, it's one of the most open-ended questions we've ever done on maths. There are lots and lots and lots of acceptable answers, which is nice. Okay. So this part is a reference to the colouring. I think it makes more sense in the Pearson VUE Test Centre. We had, of course, the left text was over there. In this version that I've got on screen, it's still up at the top somewhere. So the left text refers to all of the whole numbers being coloured red or green. But in part 4, we're just thinking about the numbers 1, 2, and 3. It's a nice Christmassy colour scheme. Here we are, red and green. Okay. So we're going to colour the numbers 1, 2, and 3. And there are different ways to do this. So you could colour 1 and 3 green and 2 red. Oh, right, okay. In which case, can you find a nice set of 2 numbers? That's a phrase, isn't it? Nice set of 2 numbers. I think that's the sort of thing where you read it and then you think about what it means. So a nice set of 2 numbers, that would mean a set with 2 numbers in it, x and y, not the same because you can't have repeats, x and y, such that there exists a target t, you can find a target t, such that the numbers can be paired together to make that target t. So that's a set with 2 numbers in it, which you can add. Well, that's any 2 numbers, isn't it? Any 2 numbers x and y, if you put them in a set, then you can set the target to be x plus y, and then pair the numbers by adding them. So I think there's a bit where you read it and it sounds very hard, and then you realise that any set of 2 numbers is a nice set of 2 numbers. I should probably mention this, but yeah. At least 2 will have the same colour. When you're colouring in 3 things, you might make 1 and 2 different, but then 3 has got to agree with 1 or the other. And if you don't even make 1 and 2 different, then we'll pick 1 and 2. Either way, and I think that is about 3 possibilities again. What was it, 26y or something? It's got 3 possibilities there for which pair it is, but 3 possibilities for which pair it's just like 26y. I hadn't noticed that. Fun. Okay, 3 possibilities for which pair it is. Pair them up, and you get a nice set. Hooray! Okay, because any set of 2 things is a nice set of 2 things. Oh, that's terrible curly brace. There we go. Let's target 5. You can pair them up to make 5. Right, okay. And then final part of the question asks you to go a little bit further. Oh, I don't like precision eraser. I need to do a lot of imprecise erasing. Final part of the question asks you to think about the numbers 1 to 27, which are coloured red or green. And to think about, maybe, if you like, hints, think about these subsets. 1 to 3, 4 to 6, and so on, 25 to 27. 3C2 possibilities is brilliant. Okay. we're going to prove that you can make a nice set of 4 numbers. So maybe you read nice set of 4 numbers and you think, oh, maybe every set of 4 numbers is a nice set of 4 numbers. But sadly not. If we've seen an example of a nice 1, 3, 4, 5 further up is not nice because you can't pair them up. There's no number t for the target. So we've got a challenge here. We've got numbers 1 to 27. We've only got 2 colours. There's 27 of them. And the hint is to put them into groups, in groups of 3. I suppose that's 9 groups of 3. We're looking for, at the end, eventually, 4 numbers that are all the same colour and that make a nice set. So something about pairing. Let's know at the end that we can pair things together. There's a few ways to do this. A few ways to argue about this. One of them is to just start at the left and to go through some cases, and there's quite a lot of cases, so that's quite a lot of work. So maybe one is red, in which case, blah. Or maybe one is green, in which case, blah. And actually, I suppose you can simplify that a tiny bit by you can halve that by saying, yeah, maybe swap all the colours in your second paragraph or something. But there's some possibilities. If 1, 2, 3, 4 are all the same colour, then haha, that's a nice set. So the colour must change at some point as you go 1, 2, 3, 4. You can do arguments like this where you say, right. So if I have a pair in a row that are the same colour, then later on, if I can find another pair in a row that are the same colour as each other, then I've got a nice set. And those things mean that you can't have, there's a tension, you can't have 4 in a row the same colour because that would be a nice set if you're trying to avoid nice sets for some reason. You can't have 4 in a row the same colour. And you also can't alternate too much, because if you alternate too much, then you can, switching between them also gives you a nice, anyway, switching back. Do I mean that? If you switch a lot, then you get something different. I've lost track of why that would give you a nice set, but there you go. Okay. I've also had day 2 is worse, but I've also had the day 1 is worse, and also we know who did day 1 and who did day 2. Yeah, calling them that. Good. Okay. 8 possible sets. Now we've got to be careful what these 8 possible sets are. This is one approach which I can see emerging in chat, which is to say that when you colour in the numbers 1, 2, 3, you have 2 choices of paint to use for 1, and then you have 2 choices of paint to use for 2, and then you have 2 choices of paint to use to colour the number 3, and overall that gives you 8 choices. 8 choices, brilliant. Okay. Of how you're going to colour in that set. Possibly your answer to part 4 was to consider all 8 of those possibilities and to identify the nice set in each case. Maybe, maybe not. Here I think the number 8 is relevant because, well, in the hint, there are 9 of these things. And there's something called pigeonhole principle, or I think to be honest at this stage, I think it's also just called common sense, where if you've got 8 possibilities and 9 things, then 2 of them pick the same possibility. I don't know which 2, but 2 of them have got to be the same. Yeah, so find the 2 that are the same, find within those, you know they have the same colour pattern, so pick the matching numbers. And then a little bit of work to convince me that that does give a nice set, that if you have red, red, green, and then after some incredible distance, maybe, a long time later, you have another red, red, green. I've just said those colours the wrong way around, haven't I? Green, green, red. If you have green, green, red, and then another green, green, red, there's a little bit of work to convince me that this really does make a nice set, that you can pair these numbers, whatever they are, up. Or similarly, if it was green, red, green, and later you found another green, red, green, there's a few other possibilities, but you know, pairing things up. To answer Anna's question, Oxford offers for interviews or invitations to interview go out at the end of November, or maybe early December, and they're sent by individual colleges. So if you have friends you're also applying to Oxford, or if you see someone else online, the emails get sent by different colleges for different subjects at different times, so it's totally possible that you'll see someone on the internet celebrating that they've got a biochemistry interview at a different college, like not at all at the same time that maths interviews from a different college are being emailed out. And that's also the date that colleges send out emails the other way around saying, sorry, but no. Not really. I'd like it if there was, but it's 29 different colleges doing maths at Oxford, and that means there's at least 29 different people doing mailings, which I'm saying late November because I know that they won't happen before. I should be saying early December, I think. Do I need to look at a calendar? Everything's late this year. Possibly I should be saying early December. It's Thursday now. 19, 20. I'm going to say early December, and we'll see how that goes. Rejections are sent at the same time too. Right, good. Okay. Pairing things up to make a nice set. There you go. Is this Callie in chat as well? Shout out to Callie, third year maths student, who is picked up on the late November, early December, which is what I said at the start, and also what I say most years. And then I thought about calendars, and I thought about time. There we go. Right, okay. Picking things. There we go. We've seen 3. We're going to see 1 more. I skipped a lot of the 6-mark part of that question. Some examples, maybe involving negative numbers. It's the meeting rooms to wrap up. This MAT Livestream bonus episode where we look at MAT questions. I just want to do a quick shout out before we go through this question. Quick shout out to chat for not being too. Occasionally people come to this one just to complain at me and just to sort of throw rocks at Slido, and I'm just going to go, thank you chat for not doing that. More pleasant than sometimes. Anyway, what do I think about laminated sheets we need to use for the maths? Time consuming and frustrating. Sorry. The dates of term are different compared to dates of Oxford term are different compared to different every year because it's different days of the week every year, but there we go. Don't take it personally, sorry. That's just me thinking about Oxford term time. It gets later. Is this true? Does it get later every year? Or does it get earlier every year? The number of days in a year is one mod 7, one more than a multiple of 7. So if I do something on like Friday every year, then the Friday is 364 days later. So Friday the 19th is followed by Friday the 18th, followed by Friday the 17th. Leap years make it move back 2 days. And then at some point the term dates shift and we go back to like +7 or something. That was not interesting. I'm really sorry for doing that. I hope people interpreted that as a kind of break in between questions, or maybe you're just reading this, which is the block of text at the top of this question, which for Pearson VUE was presented on the left, while the parts of the question appeared on the right, which is that side. What do you have advice to people to have? Oh, brilliant. Advice in chat, please, for anyone to gain a really deep understanding of mathematics. I have my own opinions, but I will let chat go first. Make sure your reply in chat is clearly saying advice or something on it, so that they know that you're replying to them. Do we get told if we get rejected pre-interview at the same time? More or less, yeah. So there's emails going out at the end of November or start of December. Either way round, sorry. I looked at the paragraph and looked away and went back to the multiple choice questions. Okay. Here we are. For 26, you said you can have 0 plus 0x to make FG, but wouldn't that not be a linear polynomial? Is that a double negative? Wouldn't that not be a linear polynomial? Let's go and check. Whee! Linear polynomials are functions of the form a plus bx with a and b real numbers. 0 plus 0x is real numbers? Yeah, I think that's fine. There was a previous version of this question, a previous draft of this question, which said that b had to be non-zero, but that's not the version that we set. Anyway. New College is the one with the Draco Malfoy tree. Why is it called the Draco Malfoy tree? I know it's in Harry Potter. There's a courtyard which has got cloisters around the outside, which is good for like walking scenes where you need some characters to walk and talk to. I don't understand movies, but you go like, oh, we need people to be walking between places. So it's like being used as Hogwarts walking between places. It's also being used in other films for just people walking around. So I think you could probably do a mega cut of like this one bit of New College of just people marching down a kind of cloister with like. It's got a roof, it's got a side, it's got a wall, but it's got like an open side with some archways into a courtyard with a bit of grass and a big tree. There's a Draco Malfoy tree. What does Draco Malfoy do with a tree? I should know this because the tree's in New College, which is the one that I teach at. If you think that b is not allowed to be zero, then I guess you missed the zero solutions, but they're not that interesting anyway. And you probably get all of the cases for the last part, I think. Yeah, because I can do those with, oh, maybe I can I? Yeah, I can do those with polynomials that don't have zero coefficient on x. So I think you can join in with most of the linear polynomial question, even if you add the restriction. Yeah, even if you add the restriction that your linear polynomials are not allowed to have b being equal to 0. The ferret incident happens at New College, does it? Amazing stuff. Right, good, okay. A negative number is allowed for 27, 3. Oh, part 3. X. Quick check. Yes. This says positive. Negative would also be allowed. Okay. Right, office building time. Office building, let's go. Said nobody ever. Hey kids, let's learn about meeting rooms. So an office building has got n meeting rooms, and they are numbered 1 to n according to their size. Meeting room 1 only has space for one person, which, is that even a meeting room? I mean, who are you meeting? Maybe it's one of those like pod things, where I stole this joke from someone else. Maybe it's one of those pod things where like you're just on your laptop on a call. Anyway, meeting room 2 has space for 2 people, which I guess does count as a meeting room, and then up to meeting room n, which has space for n people. So we have like this 1-person pod, we have this 2-person zone, and then we have this like 3-person zone ready for booking. The office also has n teams. They're also numbered 1 to n, and they call reception in order 1 by 1 to book a meeting room. For I is 1 to n, team I has size ti, so that's the size of the team. Size of the team. Oh, I've written size on the side, don't worry about it. Ti is a whole number between 1 and n, so this introduces the concept that the team could be just one person, which, is that even a team? Or as many as n. And team I calls reception there given the smallest available meeting room among meeting rooms with size greater than or equal to ti, the smallest room that they fit in. If all these rooms have already been booked, then team I do not manage to book a meeting room. So this is sad face, I think. Okay. We represent the sizes of the teams using a list, so keep track of what we've got. That's also the order they're going to phone reception, because they phone in order, 1 by 1, in that order, 1 to n. We call the list good if all teams manage to book a meeting room, and we write g of n, gn, for the number of good lists of length n. That's going to be our goal in this, is to calculate g. For example, with n is 2, the lists 1, 1, 1, 2, and 2, 1 are good, because for each of them, both teams manage to make a booking. In this case, that's a team. This is some lonely teams who book like meeting between 1 and 2. This one they book meeting between 1 and 2, and this one they book meeting rooms 2 and then 1, which is fine. Whereas the list 2, 2 is not good, because the first team takes meeting room 2, and then the second team doesn't fit in the remaining meeting room. So there are 3 good lists. And then later on, this is here so that you don't have to keep flipping between screens, but later on we'll define fnk to be the number of good lists of length n which result in the last team booking room k. Yes, right, okay. Meeting is really pushing it, yes. I also have my doubts about this team of size n is pretty pushing it, right? Because we've only got one room they fit in. I suppose there might not be a team of size n. The teams might not be size 1 to n. I suppose here's an example where they might both be really small, which would be nice because then they'd be happy with anything. Okay, right. Let's do some of this. So, first part, just down here. Is it on screen? No. Now it is. For n equals 3, explain why the list 2 on 1 is good, but the list 2 to 2 is not good. So, different ways of explaining this, I think. The one that I would go for 2 on 1 being good, is to just act it out. To just say what happens, which is team 1 picks up the phone, they've got size 2, so they get room 2. So they get room 2. I shouldn't write underneath, should I? I should write on top. They get room 2. And then this team 2, has size 1. They phone up, and they're happy with room 1. It's the smallest available meeting room among teams with size greater than equals. That's 1. And then this team phones up. They've only got one person, so they phone up. And we've only got meeting room 3. They'll have plenty of space in there, so we stick them in room 3. Yes. This team there, not size n. Right, okay. So the list 222 is not good, because, well, if I try and act it out, then this team phones up, they get room 2 again, like the previous one. And then this team phones up, and they've got the same size. That's all right. They go in room 3, the smallest room that they fit in. But then this team calls up, and I'm sad. They don't get a meeting room. They're too big to fit in the mono-person room, the pod over here. So awkward. Different way of saying that is the kind of holistic view, where you look at the list and say, none of those teams are going to go in the small room. None of them are going to be happy with that. So it doesn't actually matter how many phone calls you get through, none of them are going to end up in the tiny room. And you need one of them in each room. So, right. Okay, so we've got this kind of play bit at the start. The main reason for having this is to try and get a sense of what the setup is, what the list means. There's not that much to it. Once you work out the kind of the play, the actions that are happening, this team phones, they get a room, this team phones, they get a room, this team phones, no rooms left. I think once you've worked out that that's what it's describing, it's a pretty natural way of recording that you have some team sizes and they're calling, and these are the calls. So like maybe the receptionist is taking notes, like today I got a call of a team of size 2, a team of size 2, and then another team of size 2, oh no. That's kind of what the receptionist needs to write down to track what actually happened when we do this debrief afterwards, right? With the receptionist to be like, why is the team just in the corridor? Why are they not able to book a meeting room? Right, can't see we're working. I need to slide down. Yes, okay, well, here we go. I'm a bit worried that I've now lost all of the definition, but hopefully we've got a sense of that kind of thing that's going on. This is the sequence of team sizes who are calling, and they're given the smallest room that they fit in. Right, well, I need loads of space for this bit, don't I? Because part 2 says for n equals 3, there are 16 good lists. So G3 is 16, and we are instructed to list all of them, starting with good lists where the first team has size 1, and then good lists where the first team has size 2, and then good lists where the first team has size 3. Okay. So these are lists with 3 teams in, so it's my answer for 2. There are lists with 3 teams in it, and if team 1 has size 1, then they book room 1. They say, I'm the team, there's only one of me, so the receptionist, because they're phoning first as well, the receptionist will say, I'm putting you in the monopod. I've got several actual real teams to deal with, but you phoned first, you can have the monopod. Off you go, have fun on your own. Sad little meeting room. Anyway, never mind, off they go, that's fine. So then, in my head, I've got to keep track. I've now got rooms 2 and 3. So I could have the world's saddest office where there are just 3 separate teams who are 3 people who don't talk to each other. That works. They would get rooms 2 and 3. And then maybe I suppose I could make these teams larger so that they still get rooms 2 and 3. I suppose this one could be size 2, and then this could be a tiny team, or a middle-sized team, or a larger team. And then I've realised they could get rooms 3 and 2. That's okay. Why would that happen? So they get room 3 here in the middle of my list if they have size 3. If they have size 2, they would have been given room 2. If they have size 1, they would have been given room 2. That's all the possibilities. And then the last team, well, it's room 2 that's available at the end, so I could end this list 1 or 2. Okay, so that's the game we've got, right? So that's my list of ones starting with 1. I'm now done because, well, I've got through all of the possible sizes for that middle team. So then I'm going to list things starting with 2. In which case I've got rooms 1 and 3 left over. I'm just sort of planning out my day as a receptionist here. Maybe a team of 2 will call. I will put them in room 2, the smallest room they fit in. And then I've got rooms 1 and 3. I suppose one way of thinking about this is, how am I going to get someone in room 1? Either they call now, or maybe they call later. And then I'll have a room of size 3 to deal with. So I suppose I could fill that in by having the possible sizes. And I've already got 1, 1, so I'll put 2 or 3 in there. When is the team of 1 going to get here? I need to put somebody in this useless monopod thing. And then there's a few left which start with 3, but you can work these out but if a team of size 3 calls, then we've only got 2 tiny rooms left. So these sequences here have to be happy with rooms 1 and 2. And there's only 3 of those. Okay. The made-up stories are so important to me. Can I highlight this chat thing? The made-up stories is my way of understanding stuff. I think it often comes across as just whimsy, or me being a bit mad, or just trying too hard to make things sound weird, but it is actually my way of understanding. And I encourage this for when you, I'm sure, go on to university, either here or somewhere, to do maths at university. I encourage you to have a level of like whimsy and story to things, to make up verbs for what's going on, because actions and doing is easier to keep track of, I think, than just here are some static nouns. I need the nouns to be doing things. Maybe it's just me. It does say 16. There is no justify in this. It just says to list all of them. No justification asked for. Good. I had no clue there were 2 different map papers. Okay. Right, okay. What are we doing? We're going to think about part 3, where, here comes F. Fnk is the number of good lists with length n, which result in team n booking room k. Oh gosh, so that's team n, that's the last team, booking room k. That might or might not be the case. And this is, people in chat I saw were saying it's hard to make sense of this. I think that is the challenge. We've seen past questions like this before together, where there's something to understand, and once you've got to grips with it, for me that's through a silly story, which I thought about before we started. This isn't like me thinking of the silly story live, right? Once we thought of a kind of silly story about it, then maybe it makes more sense, and then it's broken down, and then we can just do stuff. So for me, this is the realization that it doesn't say that the team has size k. It says that the team gets room k. So there's not a list that ends with a team of size k. It's a room where they get given room k. So logic, the difference there is that the receptionist will give them room k at the end, not just if they have size k, but if they'll fit in room k. Because the receptionist at that stage at the end just has room k left and is desperately hoping that the last team to call up will fit in that available room. So it's not about the team filling the room, it's about the team fitting in the room. That last team N, that last one, make or break, here's the last one, they've just got to fit in the available room. Which, if that's room K, then they've got size. So fitting in the room K, they must fit in room K. Room K has size K, so their size is 1 or 2 or 3, doesn't matter, up to K, and it really doesn't matter. Any good list will be good so far, that we've sorted everything out so far, and then there are K possibilities for what to put on the end. Yeah, story time, isn't it? It's about the hope of the receptionist desperately on that last phone call, that last team. How big is it again? Are they going to fit in this room? I think failed is a strong word. I will remind you that if you look back at past MAT papers, the average score is not 100 and it is nowhere near 100. The test is supposed to be hard. I'm doing this really quickly and I'm trying to do all of it. That is not the experience of people in the tests generally, to do all of it and to do it all really quickly. Yeah. The first part of every trio from there. Okay, right, good. Right, so bringing it together then, because this question is trying to get us to work out G4. The final punchline at the end is to know what G4 is. And we're asked for this relationship to say how many, we're talking about how many good lists are there of length 4, and there's some link between that and the number of good lists of length 4 or n or whatever, where team n books room 1 or 2 or whatever up to n. Those are all of the rooms. Those are all of the possibilities. I would quite like that last team to book some room. I'm not actually fussy about whether they book room 1 or 2 or whatever you've got, so long as it's a good list. So I think we should add these. Skywire, chill. You're going to be okay. Everything's going to be okay. Right, yes, okay, good. So describe this relationship. I would add them, I think. And I'd probably try and justify that to myself by saying all of those Fs are good lists. I want all of them, and I don't want anything else. And they're all different, because in those different ones, Team N actually gets different rooms. So they're all different. I think I want to add those things together. This is the bit which is a bit like a recurrence relation. Okay. At the end then, we've got some calculations to relate back. We've now decided that if we can work out these F values, then we can just add them all up to get the G value and be done, which is what we're going to try and do for parts 5 and 6. Okay, here we go. And again, this is a test about understanding the things in the question. So explain why F41 is equal to G3 makes no sense unless we remember what F41 means and what G3 means. Pause. F41 means good lists, everyone gets a room. Length 4, last team gets room 1. Question mark, exclamation mark, right? The last team gets room 1? The stupid monopod thing? The room that only takes one person? Like, we can deduce something about what's going on there. Like, just the fact they've been given room 1. I mean, that means that team had size 1, right? And it also means that the monopod thing was available. That no one else took it. It's not surprising, it sucks. But the idea that small room of size 1 is available tells us something about the other teams who have called so far. It says they don't have one person. They have, I suppose, because they've successfully booked, they have size. No, we don't know the sizes. I suppose they have fit themselves into rooms 2, 3, and 4. I suppose I don't know their sizes because I don't know if they've used all the chairs in those rooms. And that's a problem with 3 rooms where none of the teams has exactly one person in, otherwise they'd go to the monopod, which is available at the end. So working backwards logically, if the last team is given the monopod thing, then, well, they have one person, they seem happy with it, good for them. Nobody else wanted it, so they're all teams that have at least 2 people, and they're taking rooms 2, 3, and 4. It's sort of the same problem as the G3 problem, the good lists of length 3. Actually explaining why it's exactly the same problem is a little bit fiddly, but I think you can convince yourself that we're sharing out 3 rooms between 3 teams, and they have to take these 3 rooms. That would be a way to convince yourself. What did I get in the math? I have never done the math. I didn't do this test. Good. Okay. So, for me, I think the description, I left it on a kind of cliffhanger there. The description, I think, for why the 2, 3, 4 case, where you know that none of the teams have size 1, the way in my head that I make that into the standard problem, the G3 problem, where you have rooms 1, 2, and 3, and teams that are going to go in those rooms, is you take these like separately. You take these rooms 2, 3, and 4, and you remove a chair from each of the rooms. That converts them, of course. Once you've taken a chair out of each room, that converts them into rooms that look like 1, 2, 3 in terms of how many chairs they've got. And you also remove a person from each team. So you get rid of some chairs and you fire someone from each team. And none of the teams had exactly one person in. So after the firing, each team has still sort of survived in some sense. And I've taken away the person and the chair, so everyone still fits. That converts it into the good lists of length 3 problem, where instead of fitting teams, none of them singletons, in rooms 2, 3, and 4, I can take a person and a chair out of each of those, and that will be a good list of length 3. The other one is more direct, and the other one here says F44. This talks about good lists of length 4, where the last team gets the big room. We know from a previous part they fit in room 4, so their size could be 1, 2, 3, or 4. It's funny to think of a singleton just turning up last and saying, "Can I have room? Whatever you've got." And they say, "Yeah, well, we've got room 4, the big board room. Off you go then. Wish you'd called first." Yeah, okay. So F44, the last team gets room 4. That means that the first 3 teams have sorted out rooms 1, 2, and 3. That one I think is more obviously good lists of length 3, right? Because up till now they've only been using rooms 1, 2, and 3, and they've sorted that out. 1, 2, 3. And then there's a 4th team called, and we don't know how big they are. We know they're in room 4, but we don't know how big they are. So that's a factor of 4 there. Good. Okay. Right. That's part 5, and then part 6. I'm not commenting on average score. I'm commenting on my attempts at doing this question. I think part 6 is harder than part 5. I mean, it's worth 4 marks instead of 3 marks, so maybe that's an obvious thing to say. But I think F42 and F43 are harder to explain. So I think I might pause here and see if anybody in chat is playing along. It's possible even if I did bad on MAT, depends how bad. We interview people with a range of MAT scores. We do look at the rest of people's applications. In general, yeah. Oh, right, okay. For part 3, it was asking about the biggest team booking room K. No, part 3. Part 3 says the number of good lists of length n. So that's like out of these ones down here. Here are some good lists of length n, which result in team n, the last one, booking room K. So for off screen, for F3, that's ones where the last team books room 3, which is not obvious from the numbers. You have to play the little game to go from 1 to that one. They book room 3. That one they book room 3. That one they end up booking room 3. In this one, they book room 3. They book room 3. They book room 3 because the first one sorted out rooms 1 and 2. In this one, they don't book room 3. They end up in room 2. The last team ends up in room 2 because somebody else has already taken room 3. In these cases, right, okay, so in these cases, they've taken rooms 1 and 2, and then these ones take room 3, and then in this case down here, they've taken rooms 2 and 3, so this person gets put in room 1, so not that one, and then this one, they've all taken room 3 straight away. So for F33, the answer would be, I think, 9. It's a multiple of 3, so a good start. It's 3 times G2, which is what's going on for the prefixes. You can look back. Right. Okay. F42 is a bit harder because in F42 we've got this kind of slightly harder logic puzzle, I would say, to work out what happened before this. And this is a logic question, really. It's not like the hats and the colours of numbers being painted and people telling the truth or lying. But this is just a sort of logic game, I think, working backwards. So you'll set some non-trivial information, and I think the reason that F is hard to understand is because it is not a straightforward bit of information to think about. It's maybe not the idea we would have if we were trying to work out G4. It's a math question guiding us, like an interview question would, guiding us through a good way of doing a question. For F4.2, working backwards, this tells me several things. Well, thinking about good lists, I can deduce several properties of these good lists, right? So this says the last team gets room 2. Okay, so immediately, if the last team gets room 2, that means they fit in room 2. So either they have size 1 or 2. It's a factor of 2, which is fair enough. It also means that room 2 was available, which means that the other rooms, 1, 3, and 4, have been taken by teams. And then we've got some deductions about why that's happened, right? It means that, well, someone's taken the monopod. So at some point, a team of size 1 has called. I think exactly one team of size 1, otherwise the second team of size 1 would have got room 2. And room 2 is available, the last team has booked it. I'm thinking about the other 3 teams at the moment. So I think there's exactly one team of size 1 who called at some point. And separately, somebody's got room 3 and somebody's got room 4. Maybe that's some teams of size 3 or a 3 and a 4. Or maybe it was a 4 then a 3. There's possibilities for how did they book rooms 3 and 4 without using room 2. And room 2 is empty at the end. It's slightly unusual because people get bumped up rooms quite often. So it means no one, either people didn't fit in room 2 or they took the smaller rooms and there weren't too many of them to get bumped up into room 2. So there's sort of loads of information you can get from thinking about when does the last team get given room 2 and when are they happy with room 2. And similarly over here, when you're thinking about the last team getting room 3, there's loads of information there. If the last team gets room 3, it means that, well, some teams have called at some point and sorted out rooms 1 and 2 at some point between them, and their sizes must be at most 2, otherwise they'd be in room 3 or something else now. And at some point, a huge team is called, and they must be probably huge because they weren't happy with room 3. So a huge team is called, and they've taken room 4. So those ones you can also argue about what's come before and what order things have happened in. So there's a lot of things. This is not quite a brute force. I don't think it's brute force really at all. I think this is deducing what the good lists look like, so that you can work out how many of these things there are. And then final point is for adding these things together. So you have several results now. You have a 16 here, you have 48 here. I can't remember the values of these things, and I don't think I'm going to work them out right now. Okay, and then add them all together. But there's this like working back logic puzzle for like, right, as soon as F is introduced, that's the kind of challenge really, is to interpret this thing where it's a list of length n. There are n teams and n rooms, and team n has been given room k. And that tells you so much about what must have happened before and about what's happening right now. That team N is booking room K. It's almost surprising how much you can deduce about the previous activities. Anyway, that's the sort of logic element of that math question. Right, okay. Exactly one table size 1, exactly one table size 4 in the other case. Yeah, no, hang on in both, because you've got to fill the... You can have 2 teams of size 1 in the second case, I think. In the first case for F4.2, exactly one team of size 1, I agree. I don't think you have to have a team of size 4. Yeah, okay. You can deduce a lot of stuff about team sizes, and then convince yourself that any order is good. Okay, for part 4. Did you to justify the team sizes for the answer? Could it be answered? Oh, the part 4 also doesn't say justify, it says describe. And it's only 1 mark. So I think for this, describe for 1 mark, sum them, add them together. add all the F's to get G, or something like that. Good. Okay, there is no such thing as a grade boundary for the MAT. There you go. I do not predict the grade boundaries. It also wouldn't be prediction because I would have all of the data, but it's not something we do anyway. Oh, part 5. Sorry, I meant part 5, and I think you're the anonymous person who asked, did you justify the team size? With the answer, could it be answered without saying about what sizes the different teams could have? I think you want to do a little bit of justification, right? It says explain why. And this one in particular, where the last team gets room 1, there's a bit fiddly. If it were me, I think I would try to justify it a bit. A good list is one where everyone gets a room. There are all these phone calls in a sequence, and if everybody gets to book a meeting room, then we call that good. Which is what we should be aiming for, I think, when our teams try to book meeting rooms. Anyway, that's the 4 questions I've got, and it's 7 o'clock, so I think I'm going to wrap up there. Thank you for joining in. Thank you for your patience with 4 different long MAT questions. I think we've done quite well there for 2 hour live stream. If you want a copy of these, it's on the MAT website. Oxford admissions process continues. The next key dates. Let's show the MAT website just because it's got everything on it, hasn't it? Oxford MAT website has got key dates on it, including November, marking MATs and making short listing decisions. So emails going out maybe late November or early December. And then if you want to scroll down, you can get past papers, which now includes the recent past, which is 2025, which has got this copy of the long questions in it. But that's been a live stream about this. Yes, good, cool. Okay, right, thank you very much. I will see you in a couple of weeks for a bonus episode about interview questions. I'm really looking forward to it. I've got an interview question from last year that's got, it's got a computer in it, but don't panic, it's not a computer science question. Looking forward to talking about that one with you all. I'll see you in a couple of weeks for that. So I did the calculation. Actually, the calculation in 336, 2 weeks? Doesn't sound right. 336, but take off 2 for the live stream. Right. Have a nice evening. Have a nice week. I will see you in 334 hours for another episode of the Oxford MAT live stream. Bye.